Now, Aldol reactions occur between two carbonyl-containing compounds. It's possible for two carbonyls to be present in one molecule, and that molecule can undergo aldol condensation reaction intramolecularly. So with all intramolecular reactions that form rings, this is one that will form a ring, that's particularly favorable for 5 and 6 membered ring formation. Remember, 5 and 6 membered rings are especially stable. So let's look at an example. We will have a few carbons here. Okay, so here we have a 6-carbon chain on carbons 2 and 5. We have a carbonyl. So we have 2 ketones. We have sodium hydroxide, so we have a base. We have heat. If you have sodium hydroxide, you can often just assume that water is also present. And let's say we're given the product this time, and we are going to explain we're going to write out the mechanism. So if you're given starting material and product and asked to draw out the mechanism, here is what the product would look like. So we're doing a full aldol condensation reaction, form a carbon-to-carbon double bond, and we still have our carbonyl in the product. Notice that we're forming a 5-membered ring. So this is a stable product. Remember, these reactions are particularly favorable for 5 and 6-membered ring formation. So when we do our first step, forming the enolate, we'll consider where to deprotonate a carbon, an alpha carbon, that will then produce a 5 or 6-membered ring. The 2 carbonyl carbons are equivalent in this molecule. They're both bonded to the same atoms, so you can work on the right side to form the enolate or on the left side. I'll work on the right side. We have 2 alpha carbons. Focusing on this carbonyl on the right. So we have our choice of alpha hydrogens here. Now, wherever we deprotonate, we will form a new bond to the other carbonyl. Let's look at both options. So first, we'll show deprotonation at this alpha carbon here. So we'll do all of that in this purple color. So we have our hydroxide, take a alpha hydrogen, and we form the enolate. So we have a negative carbon there. Our other option that we'll work through later, so let's copy this. Is to remove one of these hydrogens, and we'll form an enolate there. So we'll come back to this mechanism after we complete this mechanism up here. All right, we remove a hydrogen, we form an enolate. We'll show the negatively charged carbon in the mechanism here. So negative charge over here, and we still have our carbonyl. So now we have an enolate kind of towards the right side of the molecule and our carbonyl towards the left. So the negatively charged carbon is nucleophilic. This carbon over here is electrophilic. So those 2 carbons will form a bond and we'll break that pi bond. In the next structure, we'll have a ring because we're now connecting 2 atoms that were not previously connected directly to each other. So let's number the atoms here and make sure that we draw our ring properly. So I'll say that the negatively charged carbon is carbon number 1, 2, 3, 4, 5, and 6. So we have formed a new bond between carbons 1 and 5. We have 5 carbons that are part of the ring. So we'll draw a 5-carbon ring. I will number 1, 2, 3, 4, 5. And then let's trace where all of the other atoms are. So carbon 1 has a new bond to carbon 5, so we've shown that in the ring. Carbon 5 is bonded to a methyl group, and that's carbon 6. It's also bonded to now a negative oxygen. So this is present on carbon 5. And then on carbon 4, we have two hydrogens. Carbon 3, we have 2 hydrogens. Carbon 2, we have a carbonyl. So we draw that carbonyl in, and carbon 1 will have 2 hydrogens. So this is our intermediate here. We have a negative oxygen. So for the next step, we protonate that oxygen using water. And this is the Aldol intermediate. Next step after an Aldol intermediate is to remove another alpha hydrogen. That's the hydrogen where the original proton was removed. So that was carbon 1. That's in between the carbonyl and the alcohol. So we have 2 hydrogens here. One is removed by the base. So this base removes a hydrogen, create a negative charge on that alpha carbon. Everything else is the same in this molecule, and then in our final step, we form the carbon-to-carbon bond and remove the alcohol. So this is that final product. It's the same molecule as what is included right here. These two are the same. They're just kind of rotated and reflected. But these are the same 2 molecules. So this is the product that forms by removing the kinetic, or the hydrogen that would produce the kinetic enolate. We have a small base here, and typically that would remove the hydrogen from the CH2, so the other alpha hydrogen, or the other alpha carbon. But that would not produce the 5-membered ring. So let's also draw that mechanism, and we'll see why, when we're doing an intramolecular reaction, we'll remove the hydrogen that produces a 5 or 6-membered ring, as long as it's a hydrogen off of an alpha carbon. So if we go back and let's think about removing the other alpha hydrogen. So let's say this is option 1. And this is option 2. As far as possible alpha hydrogens that could be removed. So we've already shown the arrows here. Hydroxide removes the alpha hydrogen from the CH2 group. So we have a pair of electrons and a negative charge on this carbon. So the next step is to have the negative carbon create a new bond to the carbonyl carbon, and then the pi bond breaks. So now if we trace our carbons, or we number our carbons, we have 1, 2, 3, 4, 5, and 6. with this enolate that we formed, the new ring is between or within carbons 3, 4, and 5. So this means we only have 3 carbons in the ring. So I'll just draw a 3-membered ring here. I'll number them 1, 2, and 3, 4, and 5. And then we'll add all of our other atoms. So carbon 3 is bonded to carbon 2 and carbon 1. Carbon 2 has the carbonyl. And then carbon 4 has 2 hydrogens. Carbon 5 is bonded to a methyl and a negatively charged oxygen. Already we can see, I won't even continue the mechanism here. You can continue doing the same steps that we've done before. But already we can see that we've produced a 3-membered ring. Remember, we have angle strain. When we have a 3-membered ring, the bond angles are really small. So if we, if we draw bond angles in here, the 60-degree bond angle. But we have tetrahedral carbons as part of the 3-membered ring, and the desired angle is 109.5 degrees. So that's a tetrahedral carbon has a 109.5 degree bond angle. When carbons are in a 3-membered ring, they're locked into a 60-degree bond angle. So there's a lot of angle strain. It's very unlikely that this molecule would be produced. So if we have this as our starting material, then the more stable ring is going to form. So that more stable ring will be a 5 or 6-membered ring. Again, steps are the same. We are just adding now the enolate carb anion to a carbonyl that is part of the same molecule, and that is the intramolecular reaction.